Hello everyone, welcome back to CourseSeeded. So today we are going to solve two questions. Basically, one was the homework question from our data science lecture. Basically, in lecture 11 we did a math problem, and we were we had a definition for our mean value theorem, and we wanted to prove what it geometrically means. So we'll be solving this question to actually understand what that actually means. And we have the second question. Basically, this is based on the research which was recently done by by me. So not recently, but yes, it's been like few months. But yes, so basically a question based on that. And obviously we are going to have a second question as well based on the Shakti's algorithm. So at first we have this fx equals x square. This was the homework question basically. So you had this fx equals to x square basically from 1 to 3. Both are closed interval at 1 and 3. So closed at 1 and 3 as well. Basically, this is the closed and bounded interval between 1 to 3. Then we obviously know that MVT guarantees some C belonging to 1 comma 3, which satisfies our f dash C basically. So by MVT, basically we prove this. So f dash C equals to fb minus fa divided by b minus a, where your C belongs to this 1 comma 3. Basically this becomes open interval for that. So you have your fx equals x square on 1 comma 3, and by MVT we can write this. So we had to prove, like, we can first calculate what our C is, then we can find the geometrical meaning of what it was. So at first obviously you can easily solve this. So at first you have this 1 comma 1, basically y comma x. For x equals to 1 we have y equals to 1 as well, and for x equals to 3 we have y equals to 9. So a comma a square, and then b comma b square, which will be your 3 comma 9. So you have this, and there exists a scenes other than 1 and 3, basically in between 1 and 3, which will give us this fb minus fa divided by b minus a. So let's try to find that as well. So obviously if you know how to like find the derivative of this, then if you remember, x square can be treated as x to the power n, which is basically d of x to the power n. Basically derivative of this is equals to n times x to the power n minus 1. So we prove this for our basically those values which were rational. Basically we prove this for natural, whole number, and integer, then also for rational numbers. But we have yet to prove our theorem for basically this proof for your irrational or other numbers. So yes, basically we are just left with irrational numbers. Don't worry, we'll be proving that as well just after we have proved everything and we've done this. So we are at 1 comma 1 and 3 comma 9. So you know what that means, right? So basically we can just write x square derivative of this equals to 2x, and 2 minus 1 is 1, so I won't be writing that. Basically this is 2 times x, I'm just writing it 2x. So you have this 2x, which will be your this f dash c. Obviously c will be over here, so you can write 2c equals to your fb, which was I think 9. So 9 minus 3 divided by your this b minus a, which was your, so let's write this f dash c equals, so if you remember what your derivative was, so basically it was the slope at that point, or basically obviously we had this rate of change. If rate of change is defined at a point, then it is called the slope at that point. Otherwise, if it is defined for range b to a, then it is called slope of that range, basically of that line joining a and b. So we have this 2c, which is equals to your 9 minus 3 divided by 3 minus 1, which will be your 4. So you got this, basically you got your slope. So let me write over here, slope equals this and everything equals this. So for c equals 2, you have your y equals 4. Obviously this should have come directly from x square, and yes, so we are getting this. So after this we can write, obviously you can see your slope is equals to your this y value, but actually it's not that relevant right now. So what I wanted to say is basically, I told you to find the tangent line. So basically for tangent, we'll be just taking the slope. So slope was our 4. And if you trace the curve like fx equals to x square from 1, 1 to 3, 9, then the curves like it starts out less steep and then it goes like this. Sorry, it starts less steep. Basically, the angle is more, and then it just bends upward. So basically we go like this and we form, let's say this was your x equals to 2. So it'll go like this. And obviously if you have your this instantaneous slope or instantaneous point which was over here, so it will be like 4 over here. So obviously as you can see at x equals to, the tangent line is actually like it is perfectly parallel to the secant line connecting your endpoints, basically this 1, 1 and 3, 9. Basically you can find the slope for both of them. Well, basically there was no need to actually find it using an example. You could have just directly seen that fb minus fa by b minus a is actually your rate of change of slope, sorry, rate of change of y with respect to x. So basically delta y by delta x, basically this thing was actually equals to your slope, which is actually true. So MVT gives us the same thing which we already knew. I would say that it just gave us that this derivative is a slope. So we proved that without actually trying to prove anything. So this is the geometric definition of your MVT. So let's go with your next question, which is your bounded circuit enumeration. Let me just underline this. So at first you have the directed graph, and every edge of that graph has a unique ID. Basically in this question we don't need this unique ID, but yes, let's keep that in mind that every edge of that graph has a unique ID. If you are given that an edge may be traversed at most k equals 2 times, basically we are just taking an example, k equals 2, then find the total raw circuits following the rules given below. So basically let's say this is a graph. Let me draw it. Basically 1 to 2, then 3, then 1, 5 to 3, so 1 to 4, 4 to 5. Okay, so 1 to 4, 4 to 5, and then we have okay, so wait, let me draw it a bit more towards the right. And we have this 1 to 2, then 3, then 1. Then we have your 4. Basically it's a cycle between 4, 5, 6. So let's create that over here. 4 to 5. And then we have your 5 to 6. Then 6 to 4. And obviously as you can see 5 to 3 is also available. And then we have this 3 to 4. So if you remember, this is the exact graph we drew at that time while I was explaining this Shakti's algorithm. So we have this algorithm. So basically we just cross the bottleneck of c square times your edges. But I've already explained that, so I don't need to explain it again and again. So what you have to do, basically in this graph, start and end at the same node. So you have to take, suppose you want to start from 1, then you can you have to end at this 1 itself. So basically there are paths like 1, 4, 5, 3, 1. Basically you need to have a cycle from 1 to this 1 only. Basically if you are going to any of this node, then it should somehow connect to 1. That's what we are trying to find. Then an edge may be used at most twice. So basically we are just trying to find the cycles first which connect to 1. Basically starts from 1 and end to 1. And then we are trying to find from those nodes which are in the cycle. Basically, if there exist more cycles which we can connect, and obviously you have to keep that in mind that edge can be traversed at most k equals 2 times, basically 2 times only. So let's say we go to this 1 4 5 6 4 and then we are coming back to 5. This means we have already traversed it twice. Then we can come back to this 5 3 1. So it's a valid path. But yes, we have to find all such valid paths, or I think question says something about that. So find the total raw circuits following the rules given below. So start and end at the same node. Obviously, you have to form the cycle. Then an edge may be used at most twice. Then you can say that this is like k in our algorithm which we used at that time. So basically, we just simplified this to k equals 2. So we can basically copy paste that algorithm because it looks to me like we are just using the same thing over here. So nodes may repeat. So obviously nodes will repeat, such as 1 will always repeat because it is already said in the question that start and end at the same node. So obviously these nodes are going to repeat, and some more nodes are going to repeat. So nodes can repeat infinitely. And then avoid generating the same circuit merely by choosing a smaller starting node when e dot 2 is yes. So basically this is what we can avoid in this question, because we don't want to travel find all the paths. We just want to find the total raw circuits which are available. So instead of traveling again and again, we will just avoid them, which we did through our algorithm, and we'll be just implementing it directly from here, from where we left, and we'll be just taking 5 6 4. So basically what we are doing, we are trying to we are trying to form a cycle, and after forming that cycle we want to travel through each node whether it can form a cycle or not. Basically, if it even if it forms a cycle at itself, then also it's fine. But we have to keep that edge count in your some vector which actually counts the edge. So we can either write an algorithm which actually solves for every time. Basically that will be like c square times m, but we'll be doing it in a smart way. So let's begin. So obviously you know what you need. So basically often we write these things in your DFS. Basically we require a visited array. So this is cancelled because basically visited array for node has been cancelled. So as you can see, nodes may repeat. So we don't need this visited array for your regular DFS. And obviously we can use edge bound. Basically we can bound this edge, bounds the edge count. So basically question bounds the edge count, not your number of times you visit your nodes. So you have to keep this in mind. This is a good change, I would say. And then obviously we are going to form a vector where we'll be doing int edge visited, and then we'll be writing edge visited less than max visits. So max visits are going to be your this k equals to 2, and obviously you are going to have if your edge is 7 and you want to go from 0 1 2 1 2, then as you can see this 1 2 and 1 2 are traveled only once, but this 2 1 is traveled once more. So if this would have been 2 1 1 2 and then again 1, then also it's valid. But let's say if there was one more 2, then obviously it's going to be wrong. So you can't just travel infinitely. That's the real intention behind adding this limit for your edge. Otherwise we can obviously have infinite cycles. Basically we'll keep traveling the same cycle again and again and keep adding that. So that's the reason we need a limit somehow to limit that possibility of infinite series. So yes, and obviously I've already taught you what lexicographical pruning was. So basically this part, if e dot to less than e basically entry node, then obviously you have to like continue. So this is your lexicographical pruning. At that time I actually taught this in detail. Over here I'll just give a glimpse of what we have. So obviously it might look strange to you, and you might not be able to understand what this is. So while we'll be solving the question, I'll be explaining this as well. So obviously, suppose we start from this node 4 and we go to some 2. Obviously 2 is less than 4. So we reject it. So that's the whole idea behind this lexicographical pruning. So we can't travel from this bigger, basically bigger, since 4 is greater than this 2, we can't actually travel from 4 to 2 because it's like greater or bigger than your 2. We have to travel in the lexicographical order, or you can say the topological order. So we have this. That's not a problem to me. So I think we can start with the solution. So obviously you're going to have like a DFS. Let's calculate what all we need. According to that, we'll be writing the functions. So we have this U and entry node. So basically you will be your current node if you don't know. So basically this is the convention which we actually use. This is not like a sure shot convention, but yes, I like using U as the starting node and as the current node, and V as the parent node, and this entry node is whatever we needed. So obviously we need two more things, basically vector of your edge visits. So we can either declare them inside the global variable as the global variable, or we can just leave them as it is inside the main function. So I'll be actually doing that using global variable. Well, I just want to change the trend which we are using currently. So basically most of the competitive programs are just like fixated on using something which is like not non-profitable, I would say. So basically if you define something in the global variable, it just gives you extra space, and obviously you can call it anywhere inside the function. So at least for competitive programming, I would recommend using global variables. Obviously you can't use global variables for your security reasons on your websites or the backend which you are creating. I mean, basically the servers won't be created using your global global variables. But yes, at least for competitive programming, please use the global variables, I would say. So we have this. Obviously you can start with the transition, which I'll be telling you. Basically for every outgoing edge, so let's say from E to U, or you can say E dot U, not E to U. So basically for every outgoing edge, so if edge visits, basically if E was visited, I'll be just writing E as it is. So if E was visited and this as widget has been like greater than equals to K, then skip, basically continue. Obviously if E dot TO is less than entry node, let's call this V, then we can just skip again. Use this edge if we didn't skip with these two conditions. Then obviously if E dot TO double equals to your entry node, then we are going to like circuit found. Obviously if they are same, then we must have somehow traveled back to that point, and recursively we continue that. So obviously you can undo the edge uses or the changes whichever we made. So if you remember backtracking, recursion, and your this whatever we are using, then you can easily solve all the problems. Basically most of the problems just come through this recursion, backtracking, DP. So basically DP is an advanced version of your recursion, I would say. Basically whatever you can write in recursion, you may not be able to write that in DP, but whatever you can write in DP, you can always write that using recursion. So recursion is basically a parent of your DP, I would say. And yes, you have this backtracking as well, which just helps in everything. So you have DP and backtracking. So let's begin with what we need. So we just need these two in IOStream and vector, but let's keep everything as it is. So we have like using namespace std include, yes, so everything looks perfect. Let's just start writing the code. So we have this struct edge. Sorry, I started that inside this struct edge. Let me put a colon over here. Then we have int u, v. Basically, this is like u to v. We are traveling, and obviously we'll be taking inputs in the graph. So obviously we can have the ID as well. So basically, or we can just change how we actually think. Basically, we can do, we are going from this edge to this edge. So basically, we can just write ID n2 over here. So we have this and n, m. Then obviously we have your max visits, max visits. So let's write that k for now, which is your 2, I think. Then obviously we have your vector of edges. Sorry, vector of edges. Then sorry, we need one more vector of edge. So basically, we are just doing it smartly by going from one edge to the second edge. So we have this vector of edge, and then we have the adjacency graph. Sorry, list, which will be your complete graph. So I think we needed two more things. So we needed two more things. Let me just check what they were. Yes, so we need this edge visited. So we have this vector int edge visited. Actually, I just noticed that while I'm writing the code, while I'm typing the code, I actually start like speaking softly or slower than, like the voice gets dim, I would say. So I'll try to keep that in mind, and I will try to speak in loud voice so that you can hear always what I'm saying. So I'm sorry if you are unable to like hear me for now. So we have this current path. So I'm actually creating so just a quick info. Basically, after 2 months, you will be having a free streaming on the website, which will be like from, let me check what date today is. So basically, if it is 22 August, then you'll have your like October. So basically on 22 October or 30th October, basically in the month of October, you'll have a course launched on CourseSeeded.com. Basically www.CourseSeeded.com. Don't go to the doubts website. Go to the official CourseSeeded website. So there you can just find. So let me just tell you what I mean by that. So let's say you come over here. Then you can explore the courses. Obviously, we just want to say that newest. So we have this. Basically, this is a trial course right now. Don't purchase this. That will just, basically it's of 0 coins. So even if you purchase, it's not a problem. That course will also be for free, basically of the 0 coins. So you can just come to this page, CourseSeeded.com/catalog. Just remember this link. So after coming here, what you can do, you can sign in with your Google ID or Google account. So it will be like completely authenticated by Google. So your data will be safe with the Google. We'll be just fetching your name, whichever you have written on Google. So it will just ask for your permission, what all data info you want to share with us. So that will be there. And we are not going to ask for any phone numbers or anything. Basically, you can just log in with your permanent Google ID, whichever you use in your daily life. And then you can come over here. And what you can do after 2 months, remember that after 2 months, we'll be having like a complete master sheet of your DSA practice questions. So that will be available over here after 2 months. It's like under production, I would say. And obviously there is one more DSA course, but that's paid. So if you want to purchase, that's fine. But yeah, So the free course will be available. So just wanted to tell you that. So let's get back to our work. So we have this current path. I think the path should be vector. Oh yes, it is vector. So we have vector and current path, or we can just write as we wrote earlier. So basically CP current path, or let's write this as it is. We have the current path, and obviously if you remember, we can just take long. Okay, so instead of taking long directly, if you remember how we define your long as LL, so basically define LL as long. So you can either write like this, or you can use using LL equals to your long. And there are multiple more methods, basically type def and all. So let's write it like using LL equals to long. Basically I like this one, using LL equals to long, because it gives you more clarity of what you are actually defining. So yes. So we have this current path. Then what you can do, you can just take LL. Basically LL means long over here. If you have watched the DSA course, then obviously it's a piece of cake for you now. And then obviously you can just have total circuits, which will be your, so like it should be easy for you. So sorry, total circuits equals to 0. So let me just check what all we need. So obviously total circuits we need, and according to the question we also have to tell like all the circuits which we are going to create. So do we need length as well? Yes, so we need length as well. Basically tell the maximum number of edges in any circuit. So this will be like total circuits, how many we are getting, and the maximum number of edges in any circuit. So we can just calculating for everything in a vector, and then finding out the max of that. That will take like order of n extra time plus order of n. But yes, since we want to do that directly, so we'll be just basically we don't want to run an extra for loop. It just looks bad, I would say. Basically it won't take order of n exactly extra time, but yes, I think it will take order of n by 100 extra time. By 100 because obviously those 100 comes from like you have to like first think for your CPU how it works. So basically your CPU just defines the cache. So if you are currently running a single for loop, then in the cache you basically don't derive any extra variable. But let's say you are running a second for loop along with it, so you are giving two spaces to the same memory of the same I, and it has to like differentiate in them. So that single I which looks like it is similar over here is actually different on your CPU. So let's not go that deep. We just have like this normal knowledge. Max length, let's call this maximum length instead of max length. So we have this max length equals to 0, 0 or 0, whatever you want to say. Then we can obviously start with the DFS now. So void DFS, then we have this, sorry. So we have this void DFS. Let's say what all we need. Obviously we are going to need the basic things. Basically we had this U entry node. Obviously you can take them as long if you need, but I don't think any question in the world actually goes with long, at least for DFS not. So obviously in web design you won't be taking integer, you won't be taking int over here. You'll be basically taking objects such as integer and all. So obviously we can just skip that part right now. So we have this like entry node and U, and obviously we are going to need this adjacency list as well. So let me just copy paste this directly from here to here. So that will be like wasting less of our time. And obviously edge visits as well. So we need this as well. And obviously let me just check which one we have to call by reference and which one we have. Basically we'll first write the code, then we'll be passing anything by reference and all. And then we have this current path. So let's just paste it over here. Well, actually I should have defined that as a global variable. Then we didn't have to like waste that much time. So I think I should define, no, actually this is fine. Or let's define this in the global variable only. So we have this over here. We can define everything right over here. Then we have this, sorry. So yes, we'll obviously have to give the size basically by resize and dot resize. And obviously to assign the values such as 0 and all to every indices, we'll be just using the functions which are needed, I would say. So we can just now remove this. We basically don't need this long thing over here. Yes, so finally it looks at least readable. So we have this void dfs. Now we can just for let's say edge and e. So basically we don't need ampersand, I think, over here, but let's just keep it to be safe. Basically it helps you in your calling directly from your memory where it is saved. So but this also creates some like cache which will be like usable afterwards. So if you understand the cache, then you'll understand like half of the things in your computer science engineering. But yes, so just by understanding the definition, I don't mean you will be understanding half of the things. You actually need to implement that as well, both as a hardware engineer and as a software engineer. So half part is your hardware and half is your software. That's what computer science is actually made of. So sorry, this will be like edge visits. Then we can have your edge visits. Let's say if your E was visited, then what you can do, we can find the ID of that. So we can basically take the ID of which of these were traveled. Basically, if it was traveled from 1 to 2, then we can just take the ID. Obviously, we don't need ID if we are like using the try method. But yes, this actually, I thought right now that this is a better method. So yes, let's try this. Basically, I think it should be greater than k. Yes. So let me just check what code we wrote over here. Skip if it was greater than e dot t less than your, what is v actually? Okay, so it is entry node. So we can continue over here. Continue. So we can just either create them in a single if statement by using or statement, or condition, or we can just write them separately. So let me just write them separately, but we actually don't need anything. So e dot yo less than equals to your basically, not less than equals to, basically for equal we'll have a different thing. Yes, so over here we have the circuit found. So let me remove the equal sign. So if this is less than your entry node, then we don't want to travel this. So yes, let's continue this as well. And now we have your this use edge. So obviously we are going to use this like edge visits and all. We'll be just defining them. So edge visits. So what you can do, basically we can give the ID as the visited stuff, and what we can do, like that edge has been visited, and we have to just like mark this plus symbol. So what you can do after this, so basically you can like push back the current path as your this e.id. If you want the ID to be submitted, or you can just give from u to v that thing, but for that we will need parent command. So let's keep this like ID inserted. So ID is very useful right now. So we have this current path. So we have this cur path. I think it is cur path only. Yes. Dot pushback. But pushback is actually not that great of a practice. Basically for obvious reasons. So pushback is actually slower than your most of the things. Even emplace back when you do, it actually creates like multiple hurdles, but you can actually emplace multiple things inside a single this as a vector. So it will like add your two vectors, which is actually much better than adding the vector again and again in every loop. So what I want to say is basically if you have this pushback, it creates a reference of your complete vector. It just copies that at the back. So let me just explain it over here. So what pushback actually does in the backend. So let's say you have this vector and you want to add just a single node. Sorry. And you just want to add a single value to it, such as your 2. So it'll like travel whole of this and then come at the back of this, and it'll like insert it over here. So that's how bad your pushback is actually. So that's the reason some of the usual or good coders use queue and all. So queue top, sorry, not top. So priority queue and all of this. Basically, I haven't taught you yet. But yes. Actually, I think I've taught you, yes. Basically, in the DFS part, I've already taught you what queue and stacks were. But obviously, I haven't taught you. No, actually, I've taught you priority queue as well. I think so. So actually, I've taught you actually a decent amount of stuff. But yes, if you like purchase any course from there after 3 months, then obviously it will be like much more than this. Basically, we'll be going to actual advanced algorithms. One is this Shakti's algorithm, and basically there are 5 more algorithms. And under those 5 more algorithms, we'll have like 5 more types. So those are actually advanced algorithms. I will actually like write the names of them at the end of your DSA part, so that you can learn it from anywhere if you don't want to like get that at a single place. Well, basically I recommend learning from my from CourseSeeded website, because obviously you have learned everything from me. So yes, it just synchronizes everything. But anyways, let's begin with this. So we have this current path dot pushback e.to. Then we can just take this. If this is equals to your entry node, so should I write everything and then like just give you the code? That would be, I think, perfect. But actually, let's debug this if there is any problem. So if this is equals to your entry node, then we can just have your then we just have basically total circuits plus, and obviously we have your maximum length equals to max of your maximum length comma this. So actually let's write comma over here. Basically this is the profit of C++, but let's not use that right now. Obviously you'll have your current path dot size. Basically path dot size. Yes, so it looks perfect. So obviously you can now call the DFS over here. So we can call this DFS basically e.to, basically e.to, and in the entry node whichever you are actually picking. So we need this, So let's take edge visited equals to your so edge visited equals to your what was it again? Sorry, it is edge visits, not visited. So edge visits is basically equals to your edge visits, and whatever this ID was, basically ID of your E. Basically this is the part of your backtracking. Sorry, we don't need this. Yes, so we have this edge visits edge.id minus. And obviously you'll have to pop this as well, basically current path. So you can just pop this instead of push. Sorry, I think the push actually works normal, or the pop doesn't works normal. I mean, there was something that doesn't work normal in the backend. Currently, I don't remember because I'll have to check the backend code of your pushback and popback. It is actually order of one, but like the traversal is actually according to this complete path, even though if it is order of one. So I think the pushback is order of one. I think the popback was order of n. No, if it is order of n, then obviously we are supposed to get few more errors. So both are order of one, but yes, I'll tell you why this actually doesn't work efficiently for your memory, I would say. Basically, it copies the whole array and then it pastes this some at some cache point, and it reallocates that position, and then it tries to like implement that. So push front can work like this as well. Basically, push front is actually the worst, I think. Either it was push back or it was push front, the worst one. Anyways, what I want to say is basically you have better methods than these, and you actually use them while you're creating a website or anything. And obviously for popback, we don't need anything input inside this. This might have given us some error. Then obviously we can just define everything. I think we can take them as global variables as well. So let's keep them over here. And then we can have this. And then save this. Finally, we can just write a scene n, m. If you want, I can input the k as well, but let's not do that right now. Obviously, we can just have this as this. Sorry, what was our name actually? It was actually adjacency. So we'll have like for int I equals 0, I less than n, I plus plus. What you can do, you can basically assign this basically adjacency dot resize basically we can just resize this to n. I think so. N was, I think, our number of edges or nodes. What was it? Sorry, m is our node edges. So we have to like resize it for m. Actually, I'm getting confused right now. Yes, so basically n is your number of nodes from 1 to 6. Sorry, actually, I don't know why I just glitched. So we have this. Obviously, we are going to use plus plus I. Let's start making a good habit instead of creating few bad habits. So we have your for int I equals 0, I less than n, I plus plus. Sorry, I less than m, not n. So we have this. Then we can just like have everything according to our whatever we need. So we have like okay, so I think so. So actually don't need anything. Basically, I don't think we have an ID over here in the input, I think. Yes, so in the input, we are not giving any ID. So let's create those ID ourselves. So what you can do, you can just do like adjacency dot, I think adjacency I dot pushback. And then we can, sorry, not pushback. Since we have resized this to m, what you can do, adjacency I dot this, what were the names of the variable? So basically ID, so ID is supposed to be 1, ID is supposed to be I, and 2 is supposed to be something. So what you can do, basically you can check from where to where we are going with every adjacency. So basically we need this only for n. So we can resize this to n plus 1. And then what we can do, so we can just see in. So since we have two inputs, let's first take those inputs, int u comma v, int u comma v, and then C in U and V. Basically, I'll be just replacing them. This is just a temporary U and V. Then what we can do, adjacency, basically U dot pushback. So we have this adjacency U dot pushback. Basically, so we need like this, and what we can do, we can just add this V comma, sorry, not V. I think, yes. So we took edge over here, and so that means we have to like extract the edge above this first thing. Secondly, second thing we have to like, since this is an edge and this is a vector of edge, so we'll be just calling adjacency I, which will be a vector again. So to call something inside that, we'll have to call the second vector, which will be your V, sorry, I or J, whatever it is. So after that, so we can push anything inside that vector. So dot push back. Basically, these two things will be pushed, ID and 2. Okay, so I finally got it how to do this. So basically, adjacency U dot pushback. Then we can just use I comma V. So basically, this bracket tells us that we have to push this as a vector. So don't worry about that. I hope this is correct because this actually looks very intimidating. Anyways, so let's remove this return 0 for now, and then we have this for int equals 0. So basically, the thinking that I'm creating is basically very basic. If you know everything, so it's nothing like advanced or anything. It's just the basic stuff. The advanced thinking is basically how you deploy this DFS, which is okay. Sorry. Yes, so it looks correct. I thought this was supposed to be less than entry node. Yes, so basically how you deploy this DFS and how you call this, whether backtracking is needed or not. So you have to just think whether this is needed or not. Rest of the things are actually done by the algorithms. So you don't actually have to like even remember the algorithms. You can just write them down in a single place, and then you can just keep seeing that from that place, and you can keep writing the code. You just have to think whether you have to put that algorithm over here or not. So that is basically called the prediction, which we'll be creating in our prediction model of our AI. But we are obviously creating normal AI, not like jumbo AI, I would say, because that requires a lots of effort and money, obviously. So we have this for int I equals 1, sorry, not 0. Basically, we have this adjacency dot resize the n plus 1, so we're just doing this. So from 0 to m, then we have this I plus plus. Adjacency U dot pushback. This will actually, this is actually not good, I would say, because we are actually going for m sizes and we are like pushing this m times. So let me just create this m plus 1. But actually we don't need m plus 1 because this U will carry everything. Basically what are, basically tell what we can go. Basically from 1 to 4 we can go, 1 to 2 we can go, and 2 to 3 we can go. That all is basically defined by this. Okay, so this is n plus 1 only. Sorry, my bad. Basically this U we are taking input over here, and you will just define it how we need this. So anyways, we have this int I equals 1. Then we have this like I less than equals to n, I plus plus. Then obviously sorry, this, let's create this plus plus I. So even I have got actually this bad habit, at least while I'm writing the CP code for the competitive programming, it actually is a habit of mine to like take I plus plus instead of plus plus I. So we have this current path dot clear. So basically why are we clearing this path? So that we can get a fresh path for our next I. Basically if we are traveling from another node, so we can just have a fresh current path vector for that. And then obviously you can just push back this current dot push back, or we can just call this node node equals to 1, and then we can just go to node less than equals to n, and then node plus plus node. So basically these are your nodes. So now it will be easier to push back node. So we have finally almost solved this. Then we are just over here, we'll just call this DFS, which will be your DFS as start comma start. Sorry, not yes. So this will be your DFS. Basically it will be equal to your this e dot 2 is double equals to your is equal to your entry node. So it will just give this total circuits plus and then everything. So we have to like create that. So sorry, I actually had some someone visiting, so I didn't want you to capture their sound, so I just like loudly said anything. So anyways, so we have, so like we have this okay, so let's, I forgot where I was. So we have this void DFS. So we have this current part dot pop back, and we have, so okay, so our DFS was completed. I think everything was completed. So just we need to run the code now. Let me just see out total circuits. Sorry again. So total circuits. Let me just see what our name is. So basically total circuits and maximum length. So we are not going to print anything else. You can just do it yourself later, because people over someone has like arrived. So I actually can't do it properly. I need to rush things because of obvious reasons. So thank you everyone. Like thank you for joining. Let's just check the answer and let's move out of this. Obviously, even if this doesn't work correctly, I'll be just like giving you a correct link for these things. Okay, so we missed a colon, sorry, semicolon. 26th line, we missed a colon. Okay, so that looks correct. Okay, so this was supposed to be current path, not current path. Where is it? I actually need to rush things because of obvious reasons. Okay, so we have this current path. Then we have your this. We have 49 and 48. Just wait a second. We just need. Okay, so finally it looks good. Let me just print this. Okay, so 32. So we got just this last thing, which will be conflicting parameter const. Well, let me just check. So we have this. Oh, okay. So size is actually like your something. Basically, it is not maximum. So we'll be just doing this LL over here. Let's do this. I hope this doesn't give us any problem. Just the last thing, which is your DFS start, comma start. Okay, so this was supposed to be node, not start. Node, comma node. I hope we got everything correct. Okay, so I wrote CUUR instead of CURR. Current path actually, not only just this. So current path dot pushback. I hope we have corrected everything. Basically, logic you understood, right? So you can just write anything, whichever you need by your own. So let me just write this input over here. Just it will create few problems. Let me just. So we have this path. Okay, so input. So we have this input, which will be. So it's a small input, so don't worry. I'll be just taking a few more minutes of yours. So 1 2, basically 2 3, then 3 1, then you'll be going with 1 4, then you'll be going with your 4 5 5 6 6 4, then you have your 5 3, then you have your 3 4. We can just copy this, and after copying this we can just paste it over there. Yes, so finally it looks great. Okay, so we can finally paste this, enter, and we didn't get any output. That's not what I expected. Actually we should have got at least 0 or any output, but okay, so let me just debug this. ./p31. So yes, this is actually perfect right now. p31.cpp, and it actually took the input, but it didn't give us, wait, just wait, 3 4 3 4. Okay, so it didn't give us any output. Let me create a text as well. Basically total circuits. So you have total circuits, then we have your this maximum length, which will be your maximum length. Actually I can't hold for much longer than this. Let's see what we get. Okay, so I didn't choose any size. I think that's the problem. I think. So obviously we need this n and m as well. Okay, so we have this 6 and 9, I think. Yes, so we have 6 nodes and 9 this. We can finally this just copy this. Press shift enter. I hope yes, finally we got it. Okay, so it's still not giving us any answer. So we have 6 nodes, and then we have this. Okay, so we didn't resize any this current and all. So let's assign them some values as well. So let's say we have this edge visits. Dot assign. I actually forgot to assign. Then m comma 0. Then obviously you need to assign some values to your current path as well. Sorry, not current path, because we are, I think, pushing. Yes, so pushback and pushback. Yes. So yes, finally we are good. So let's just enter and paste. Yes, so we finally got the answer. So first you have this 29, then you have your 13 as the maximum length. I don't know whether it is correct, and I actually don't have the time to check whether it is correct. So let's just quickly check whether it is correct or not. So total circuits I don't know, but let's check for the maximum length. So we can go from 1 to 4. Then we can go to this. Basically, let's just see out that directly. Current path for auto. Let's do this current path. Then we can just have your cout x. So just yes. So yes, we got what the. Okay, this was actually surprising, I would say. Okay, so we actually just popped everything over here, so it will actually not create something which we can print. So what should I do? Okay, so before popping, either we can just add that as a path, or we can just leave it. So anyways, we don't need this. Well, basically, let me just quickly check manually, because if I start thinking about that, then it'll take, I think, even more time. So we have this 1 2, then we have this 3, then we have your 4, then from 4 you can go to 5, and then from 5 you can go to 6. Okay, 6, then we can come back to 4, and obviously from 3 you can go back to 1, and from 1 you can go back to 4. So let's try to create everything. Basically 1 2 3 4 5 6 7. Okay, so that will not give us the answer. Let's try from 1. So basically 1 2 3 4. That will also not give us any answer. So basically this is kind of useless for us, this 4 5 6. Basically 4 is useful, 4 might be useful, or I think even this is not useful to us. So we have this 1 2 3. I don't know how we are getting maximum length as this 13. Okay, so I think 1 2 3 is useless. So basically we have this 1 4, and then we have your okay, so from 5 we can go to 3 as well. Sorry, So basically 1 to 2, then going to 3, then we can go to 4, then we can go to 5, then 6, then 4, 2 came once, 3, 2, 3, okay, so 4, 5, this is 6, 4, okay. So we have 1, 2, 3, 4, 5, 6, 4. Then we can either come, yes, we have only one option. We can come back to 5. 4, 5 is traveled twice now. Then we can either travel to 5, 6 and 6, 4 again, but that will create some problem because we can't travel this again. So we won't be going in that direction. So we have this 1, 2, 3, 4, 5, 6, 4, 5. Then we can go to 3. Then we can go over here. 4, 5. No, so that will actually create some problem. So okay, we are just at 3. Then we can come back to either 1 or we can, yes, so we can go back to 1 from here. So let's see how many lines we have. 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically 4, there must be some 4 extra lines, but which I am not able to get over here. So what we can do is, okay, so let's leave it for over here because the answer must be correct, obviously. Actually, I haven't checked the answer. I'm so sorry for that. So thank you everyone. Thank you for joining. Let's meet later after this. So basically, if you remember what I told you yesterday, basically we created a data science library, basically a small perceptron type thing. Basically, it's not even a complete perceptron, but yes, we created it completely using our maths. So those who like remained throughout the data science course, they were able to actually build something. So I would recommend checking that out if you haven't checked the data science course. So thank you everyone. Thank you for joining. So let's meet with our 3 videos in a week schedule. Bye bye. Take care. And please solve few more questions based on this. Bye bye.